Let us start a short session on this chapter, logarithms. Right. So logarithms is not something which from which you are likely to get a direct question in the examination, but logarithms is something which will be used in a lot of calculations. So we will be looking at a few fundamental properties and few important things as far as logarithms are concerned. So first, let's understand what this exponential function and the logarithmic function is. So f of x equal to a power x, where your a is greater than 0 and a is not equal to 1. So f of x is the denotation for a function, right? That's how a function is denoted. And your x is basically the variable. So it's something like y is equal to a power x, wherein your x is the input. You'll keep giving values to x, and in return a power x will keep giving you values which you will assign to y. So your y is your output and your x is the input, right? Remember, for a function to be exponential, your a has to be greater than 0. So this a that you see, the base can't be negative. Also, the base can't be equal to 1, right? Because if the base is equal to 1, then you'll have a flat straight line, because everything that you will give 1 power anything is 1 only, right? So your a shouldn't be equal to 1 and your a shouldn't be so now that your a is greater than 0 and not equal to 1, then your function will look something like this. The graph will be something like this. The domain of this is R. So domain means those values which I can give to x. So allowed inputs is basically your domain, right? As I told you, your x is the input and a power x is the output, right? So basically range is your output, or I should say possible outputs for these allowed inputs. So every input will have its own output. So the set of all those allowed inputs is basically called your domain. And when you make a set of the allowed outputs, so you give an input, you get an output. You give an input, you get an output. If you collect all these outputs for all these given inputs, then you get the range, and that is basically your allowed output. So for this function, the range that exists is 0 to infinity. So for instance, a power x, if I make x a highly negative number, so something like a power minus 200. So that will be 1 by a power 200. That's a very small value which is almost equal to 0. That's why you have this curve which is tending to 0, but it is still not 0. So that's the reason why I didn't write the range as 0 to infinity. Like I didn't include 0, because that will become wrong. I can't get a 0, but the value will keep coming closer and closer to 0. So that is the reason why you have this open bracket. So 0 to infinity. So as you keep increasing the value of x, you keep getting bigger and bigger value, right? So that's basically your exponential function. Also, if your a is actually less than 1, you'll have a different graph. So frankly, this graph is for a greater than 1, right? A greater than 1. For a less than 1, the graph will look something like this. It will be something like this. So you'll still have a 0, 1, but as you can see, this is an increasing graph. For a less than 1, you'll have a decreasing one. Let's look at why this happens, because that will help you keeping this fact in mind. So for example, if you have something like 0.2, right? So 0.2 is a value which is less than 1. If I keep increasing 0.2, like if I do 0.2 power 10, so basically 0.2 is 2 by 10, right? 2 by 10 power 10 is a very, very small value. But if I do 0.2 power minus 5, that is like 2 by 10 power minus 5, which is like 10 by 2 power 5. Now this is a huge value. So if you are going towards the negative x, if you are giving negative inputs for a less than 1, then you are getting a bigger value. So that's why you have it tending to infinity for values x less than 0, and you have it tending to 0 for values of x greater than 0, right? So if your exponent is less than 1 and then you are giving positive values, the more and more bigger value that you give, the lesser output you get. And the more and more negative input you give, the bigger output you get. So that's the reason why the graph will look something like this for a less than 1. So with this exponential function, then let's look at this logarithmic function, and most of our chapter is basically on this particular function. It's denoted by f of x equal to log x base a. So if for instance, if you have something like a power y is equal to x, or rather, if you have something like, yeah, exactly, something like x equal to a power y. Now, if you are given the value of x, and also if you are given the value of a, can you find y? Right, so something like, if you have 2, you know 2 power 3 is 8. But if you know 2 and if you know 8, and if I ask you to find what 3 is, or if I ask you to find for what value of y will I get 8, right? So this function helps us in doing that. So what we basically do is we write something like log x base a equal to y, where this y is your exponent, this a is the base, and this x is the value. So remember, your log x base a, this f of x is the exponent, the a is the base, and your x is the value. So for what base power value is equal to base power exponent is equal to value. So if I have value with me, if I have base with me, how do I find the exponent which will make this equation valid? That will be using this function called logarithmic function, right? In fact, this function is the inverse of the exponential function, right? So you learn about inverse functions in detail when you study the chapter functions. But as of now, I would like to tell you that if a function's graph is like this, f of x, then its inverse will look something like this, f inverse x, right? Because the graph for inverse is just a mirror image about the line y equal to x. So if you have a function's graph given with you, and if you treat y equal to x as a mirror, then the mirror image that you get is the graph for the inverse of the function. So logarithmic function is the inverse. So if I have a mirror here, then it will look something like this, right? So your logarithmic function, as you can see, is looking something like this. So its domain is 0 to infinity. That means the value, this x that I give, it can't be negative, right? So whenever I have function y equal to log x base a, x can't take negative values, it has to take positive values only. Also the range. The possible outputs are anything between minus infinity to infinity. So something like, if I have log 3 x, so if my x is less than 3, for example, if your x is 1, right? So it's basically, if I have, for example, let it be x, right? So how do I write this as my known form? This is my base, so base power exponent is y is equal to x, right? Is equal to value, base power exponent equal to value. Now, if your x is less than 3, if your x is for instance 2, then your y has to be negative, right? Because if it is anything positive, then this is not valid, right? It can't happen. So in fact, if it is even lesser than, as you keep decreasing this 2 to something like a 0, and if you keep decreasing it furthermore, like you can't go below 0, obviously. So if you have something like a 0.1, then this y is definitely negative. For 3 power y equal to 2, it can still be something like a 0.2. It can still be positive, right? But for something like 3 power y equal to 0.1, y has to be negative. That's why you can get negative, and y was your output, remember. So this is not my function. My function is here, where my y is the output. So it can still be negative values. So that's why you have this edge which is of negative values. And if you put y is equal to 0, then 3 power 0 will be 1. So your x coordinate will be 1. So that's why it's striking the x-axis at 1, 0. And obviously, if you keep increasing the value of x, the value of y goes on increasing, right? So it's very, very simple. If your x is less than 1, then y, which is your output, will be negative, right? So between 0 and 1, between 0 and 1, your y traces everything between minus infinity to 0, right? So between this x being 0 and 1, your y traces your output. So this is your input. Input is between 0 and 1. The output traces everything between minus infinity to 0, right? Everything between minus infinity to 0 in this much region itself. And after that, after x equal to 1, if you keep increasing it, the value of y will just go on increasing. So this was all about your logarithmic function. Let's move on to the next subtopic. In fact, there's one more thing that I would like to tell you. This graph is also valid for, this graph also is actually valid only when your a is greater than 1. So you can still have cases where your a is between 0 and 1, right? So this graph that you see is only valid when a is greater than 1. But what if your exponent is between 0 and 1? So once again, it will be something similar, but you'll have a decreasing function. So this is how the graph will look for a in between 0 and 1. So for a greater than 1, it's an increasing function, and for a between 0 and 1, it is a decreasing function. And if you want to prove why it will be like that, so you have y equal to log x base a, and you already know that this can be written as exponent power base power exponent equal to value. If your base is less than 1, right? If your base is less than 1, then negative values of y will give a bigger value of x. So for example, something like a 0.1 power 100 is much lesser than 0.1 power minus 100, because 0.1 power minus 100 means 1 by 10 whole power minus 100, which is 10 power 100, which is huge. So as your y becomes more and more negative, your x becomes more and more bigger, right? That's why your curve is like this. And as your y becomes bigger and bigger, your x becomes even more lesser according to this. And that's all when your a is between 0 and 1. So that's why this is the graph. This is the graph when your a is between 0 and 1. And this is the graph for log x when your a is greater than 1. So with this, let's move on to the next subtopic.